at some more stuff in this diagram. Now I mentioned that normal pages are 4 kilobytes in size. Now large pages for x86 with PAE is 2 megabytes in size. Can anyone spot here something that looks like 2 megabytes? Can you guess how large pages are mapped? If anyone can guess, please type in chat. If not, I will just say it. So where did that 2 megabyte come from? And the idea here is that if we take these 12 bits and add these 9 bits, we get 21 bits. 21 bits is exactly 2 megabytes. And so how is a large page mapped? It simply means that the PDE points directly to RAM, and these 21 bits become the offset. And so the main advantage we can see here for large page is that a single entry, let's say in the TLB cache, can point to a 2 megabyte chunk of memory instead of just 4 kilobytes. And in fact, it means we don't need a page table. Exactly, there's less lookup and the cache is better. So this is the main benefit of having a large page, just so you know. Okay, so we looked at that. Now we're not done. This is just an example showing you how a valid x86 PTE or PDE looks like. So here's the valid bit. This is the bit that currently is 1. When it's 1, these bits are used in the way that's kind of briefly described. Here's the PFN with its 24 bits that is then added to the 12 bits for a normal page. Here you can see there's a flag for a large page, so that the translation mechanism, the CPU knows not to go another level, but say, okay, PDE is enough. I'm not going to check another level. I'm just going to add the larger offset. And there's some other bits here which are not too important for our purposes. If you want the exact details, you can check out some of Intel's manuals which describe these bits in details. Some of them are used by Windows, such as the copy on write bit and stuff like that. In any case, if we look at 64-bit address translation, which is what we have today, this is what it looks like. It looks a bit scary, but it is exactly the same idea, just extended to 48 bits. And so now there's no single page directory pointer. In fact, there are many of them, or could be many of them, and there's a single instance of something called page map level 4. So Intel finally realized that trying to come up with new names for these data structures is becoming futile, and so they started resorting to numbers, which makes sense. This is level 4. That's level 3, that's level 2, that's level 1. And so the next level is going to be page map level 5, which is the way things work with SunnyCove, as I mentioned already. And now you also understand where did that 57 number come from. Because we have 48 bits, and now if you want to add a full-blown data structure, then we have to have 9 bits more, because each entry is still 64 bits. And so 48 plus 9, that's 57. That's how we get that 57. And so the extension to this scheme is just having yet another single instance of something called page map level 5, pointing to potentially 512 page map level 4 instances, each of which points to one of 512 potential page directory pointers, and so on and so forth. And so you understand that the fact that we are using a 64-bit system also means that the number of these page tables, directories, and so on also grows. And grows depending on the amount of address space we're currently using. And so there's a cost to having a 64-bit system. The translation scheme requires more indirection, which means it also requires more time. So we have to have these things. And so again, This makes the TLB cache even more important in practice. I also mentioned at the beginning of this module that there is a huge page, and the size of a huge page is 1 gigabyte. So can anyone see the 1 gigabyte here? So this is the same idea as with the large page. Let's take another level out. And so if we take 12 bits and then 9 and 9 again, that's 30 bits, which is exactly 1 gigabyte. And so the way huge pages work is that they're mapped from the page directory pointer directly to RAM using the other 30 bits as offset. And again, this means less lookup. And it also means that a single TLB entry can map 1 gigabyte of address space in one entry, which is better. So this is the advantage of using these large or huge pages. I haven't yet described when they're actually used in Windows, but conceptually, if they're used, these are the advantages we expect. That's less lookup and better use of the TLB cache. And so is the addresses of these directory tables randomized? And well, on Windows 10, where ASLR exists in the kernel, the answer is yes. Previously, not necessarily so. But again, it's fairly unpredictable because it depends on which process does allocate memory and so on. And so that's PTE base from, yes, so on 32-bit. That was the case. In any case, today on 64-bit, there's ASLR. It doesn't exist on 32-bit because there's not much range to play around with, but these areas change every time you boot the system. And so technically, if you're thinking, well, if I'm in the kernel, I can change any one of these data structures, I can then change the way things are pointed to, and this is correct. You could do that. But if you're in the kernel, it doesn't matter much because you can access any memory of any process anyway, so I'm not sure that is important enough, but still the option exists. So what about the kernel debugger? Can we see some of this stuff in the kernel debugger? And of course the answer is yes, so let's take a brief look at that. So when we look at local kernel debugging or remote kernel debugging, we need to look at kernel debugging anyway. There's no way to do that from user mode. In user mode, there's no way to know where a virtual address points to. And even if I knew where a virtual address points to in physical memory, that would be of no use to me. There's no way I can get to that physical memory directly anyway. So there's no point. And even in the kernel, the almighty kernel, there's no way to get into a physical page directly. It always has to be done indirectly by mapping a virtual address to the physical page in question. So there's no way, because the CPU is in such a mode when it does not recognize physical pages as direct access. It only recognizes these tables that it expects to find properly provided. And so let me discuss some of the stuff related to what we've seen here. So let me start by looking at some process. So let's looking at Explorer. And one of the pieces of information that we've seen, and I mentioned that briefly when we looked at that in the first module, but now it's a better chance to look at that in detail, is this dir base parameter. This dir base is exactly where that single structure, that page map level 4 starts. So this is where it is in physical memory. Remember that this structure is always in RAM. You can't get rid of it because if it's not in RAM, how would you get to that? And so the page map level 4 is always in RAM. The other data structures, by the way, can be theoretically paged out. That's completely fine, and it's handled normally because every one of these entries has a valid bit just like anyone else, and so it is possible to have these page tables, page directories, and so on. Anything that is not the root of the translation, they could be paged out, but the page map level 4 cannot be paged out. That can never happen. And so this is the address of that page directory in physical memory. So you technically can take this address and examine that. So we looked at commands such as db, but DB works with virtual addresses. In this case, we need to use another command called BankDB. BankDB allows us to look at RAM, at physical memory. So we can look at any physical address that we want. And so we can technically take a look at this address and look what's going on there. And so this would be these entries that are part of these 512 entries here that point to some page directory pointers and so on. So technically, you can try to follow these information and build something out of it. To make things a little easier, you can use the PTE command to provide a virtual address for which the kernel will go to these tables for you and get to the appropriate address in physical memory, and also show you the various values that in these translation units. So you need to provide some virtual address to that. Now, naturally, if you're using a kernel address, then that's of course fine, because that's absolute. I can take, for example, just the eProcess as an example. It doesn't matter. I can take any kernel address that is valid and give it to the PTE command. And so what we see here is that we do get proper information describing the various data tables here, because we're using now 64-bit system. So we have these entries, these 4 entries here. 4 numbers, we can see these numbers here. This is where it is in a virtual memory, and this is what it contains. And so technically we can try to interpret that. And eventually we can see here it points to somewhere in RAM. So this PFN, page frame number, is the page in RAM. And so the actual address where this value should be is 659D with 3 zeros, because that's the actual address in physical memory, because the PFN is always a multiple of pages. And so here we can also see in this case is that in fact this PDE points to a large page. So there is no, technically there is no PTE here, because it's not needed. A PDE points to the final PFN anyway. And so the final PFN is here. This is where the page is in RAM. So technically, if everything is correct, and I go ahead and look at the address from a virtual perspective, that's the address of the eProcess I selected earlier, and I go ahead and look at this address from the physical perspective by taking this number and adding 3 zeros, but not really 3 zeros, because notice we have an offset here of 80, so I have to match the offset. I should be able to see the same result exactly. We can see this is exactly the same values. Here's 03, 00. You can see it's exactly the same thing, because this is where it is currently in physical memory. So you can always try these things out. Here we can see the value, the various flags here. Here's the valid bit that says, hey, this is a valid page directory. It means it points to somewhere real. It's not something which is paged out. And I explicitly selected these eProcess objects, which are normally non-paged. And so it's easy to see that. If it were paged, we won't see this valid bit. It will not exist. And then it will stop. The interpretation of these values will simply stop. Another way to go about it is use the V2P command. V2P allows you to translate very easily to get to all the calculation that I've done manually by giving it a virtual address and giving you back the physical address. And so V2P needs not just the virtual address, but also the directory base for the process, because it must match it to the appropriate process. And so in our case, because we're trying to translate an address which is in system space, we need the dir base of the system process. So I'll first list the process 00 with the system process. We can see it has this dir base. And so what I need to do now is use V2P, provide the dir base, and then the address in question. So the address is this one. I want to get to the same values, hopefully. So I'm going to paste that address. Let the debugger finish its previous operation, then try it out. And so what we see here is that we have these same values that are given us here in shorthand notation without any specific indication of flags and stuff like that. So we only see all these various levels of translation. This is the level 4 and PDE and so on. And this is large page, so it mapped to this physical page. So this is the physical address. And notice this is the same one I used right here in the DB command. So it's exactly the same one. So VDP is an easy way to make this translation without going through the actual details of every level there. And so two ways of doing something which is very similar. And of course, we can do that on a process by process basis by taking the dir base of that process, which is the page map level 4 for that particular process, which is always available. So I hope you kind of understand how these things work. That's right. So every kernel address will actually share the same dir base of the system process. That is correct, because they're part of that same address space. For normal processes, each one would have its own dir base. That is correct. And then one of the exercises in the labs later on allow you to test these things, to try it out yourself, whether on kernel addresses or user mode addresses. And so we can just try it out and see how that works. But here you can see a good example of it working properly. You can start with these eProcess addresses, which are always valid and always in RAM, should be always paged in, and so you can start with something which is always valid. But then you can test out any other address that you want and see what output you get. So I'll leave you to do that later on. Okay, and so if we look at the valid x64 PDE or PTE, this is exactly the same idea, but this time the PFN length is 36 bits, because 36 plus 12 gives you the entire 48 bits, which is currently supported by the hardware. But there are several bits here which are still reserved, which allow us to use more PFN bits. For example, in the Sannikov case, we'll be using another 9 bits here to extend the PFN to be 45 bits, so that 45 plus 12 will give us the 57 bits that are supported by Sannikov architecture. The same bits apply here as well. There's the valid bit and some other bits like the large page and so on. So this is not really much different than earlier. Okay, so this is the idea of translation. It happens all the time. There's no way around it. And in fact, it has many benefits, of course, such as the ability to share memory. I can point two virtual addresses for different processes to the same physical memory. And so this is only possible to do with virtual addresses. Otherwise, it wouldn't be possible. Each one would have to have its own kind of physical pages or something. And so we looked at what happens when the valid bit is true. And I mentioned what happens when valid bit is false. Then we have a page fault on our hands. So a page fault from the CPU's perspective is just valid bit of 0. But the result of that page fault may be different depending on what actually is pointed to by that memory address. So for example, what happens if I access address 0 in the virtual address space in my process? I already mentioned that this address it can never be committed. So because everything is 0, then that particular page table probably will not exist. And so a page fault will be thrown immediately by the CPU. And so in this case, the memory manager will say, hey, there's nothing there. There's really nothing there. And the memory manager will convert that page fault into an access violation exception and send it back to the process for possible handling using the normal structured exception mechanism we discussed already. And so not every page fault is actually fixable. Only some of them can be fixed if they are in fact a valid operation, such as a page being in a page file. Okay, and so what I want to show you now is some types of handling for page faults and how are they used. In general, Windows tries to distinguish between two types of page faults. One of them is hard page fault, which requires disk access, and this is by far the worst one because disk access is naturally very, very slow. On the other hand, some page faults are soft page faults which do not require disk access but can still be resolved. A classic example is using a DLL. So let's say you have one process using kernel32.dll. Now I'm creating a new process that also maps kernel32.dll. And now it wants to execute a code inside the DLL. Do I have to load the DLL's code from the file again? No, because it's already mapped into physical memory. It's already been used by multiple processes. All I have to do is change the valid bit to change the page tables to point to the existing memory and tell the CPU try again. So no I/O is required in that regard. However, conversely, when you load a file for the first time for execution, such as a DLL or an executable, a hard page fault is unavoidable because it's not in RAM yet. So the first time it has to be mapped, but since it's shared, we can share the code with other processes without needing to read that code again. That's a good thing. So here are some reasons that cause a page fault to happen and how the memory manager handles them. So the classic case is when we access a page that is not in RAM, but it is in a page file or a mapped file. So maybe a DLL wasn't used for a long time, and so its code just went away, and now we need to use that code, and so we can go ahead and read that code again. And so that's fine. If it's a data page, maybe stored in the page file, then the memory manager will do what needs to be done, get the data from the disk, put it in RAM, fix the tables as needed, change the valid bit back to 1, and tell the processor to try again. This is a normal, successful way of handling a page fault. But there's actually other options here. So let me describe some of them. So one thing which may be not that difficult to understand is that we're actually accessing a page which is read-only. So this is a page fault. The memory manager says, hey, that's page read-only, try to write to that. That's not a good idea. It turns the exception back into access violation. And some other stuff like accessing kernel memory from user mode, that's not allowed, access violation. And it can be the case where we're accessing a page that was never committed, so there's nothing there. And so the valid bit is 0, or maybe that page table or page directory doesn't even exist. And so that's an automatic page fault, and the memory manager says, hey, there's nothing there, I have nothing to do here, but throw an access violation. Another more interesting thing is called the demand 0 page. So this is the case where we commit memory, but we're not touching that memory yet. And so let's look at a quick example. So here's our sort of junk code. Let's say I have an application. I'm going to use the virtual alloc to reserve and commit a large memory space. Let's say 1 GB. And so the first parameter to virtual alloc says in which address do I want to make the operation. I'm going to specify null here, saying I don't really care, just find me a free location. And then the size will be 1 GB, that 2 to the 30th power. And then it's going to be mem reserve and mem commit. You need to specify both flags. Technically, you can specify mem commit only, but that's not correct. But the Windows API allows you to do that because of a bug that existed in all the versions of Windows, people using mem commit when it shouldn't have worked, but it did work. So once Microsoft realized it was a bug, they decided not to fix it so that the old code will not break. But the correct way to commit memory up front is by using reserve and commit. So once I do that, I get back a pointer to that block of memory. So what does it mean to commit a memory here? Does that mean that 1 GB of RAM is going to be now allocated for me and mapped using the virtual address range that I currently committed? No, that's going to be wasteful. The fact that I'm committing memory means that the commit size that we see here, the commit size will increase by 1 GB immediately, which really says that if you need that 1 GB in its entirety, you're guaranteed to get it. but the memory manager doesn't go and immediately create 1 GB of RAM and map it to your address space. That simply would be wasteful. Instead, once I do something with the memory, so let's say I decide to write to that memory some value, then touching that memory will actually cause a page fault, and that page fault is a demand 0 page fault. So the page table entry exists, but it has a special flag saying, hey, that's a demand 0 page. And so this is the time the memory manager will provide a zeroed page to the working set of the process. So it will provide a 0 page in RAM and point the page table entry to that page and tell the CPU, try again. And so this is called the demand 0 page. And we'll understand why the page should be zeroed in few slides when we discuss how physical memory is handled. And so you can understand all these cases of page fault. So in essence, copy and write is also kind of page fault, because you're accessing some memory that the memory manager needs to know about. And so again, the CPU throws an exception. And so you go ahead as a memory manager and take care of that by creating a private copy for that particular page, for the particular process, and so on. But from the CPU's perspective, again, page fault is just 0 in the value bit. There's really nothing else. All the rest is taken care of by the memory manager. And so if you have a PTE which is invalid, so zero memory macro, no, zero memory macro is just using memset to write zeros to any range of virtual address space, which of course writes that to RAM as well, because now you are forced to have this memory in RAM. So it doesn't really concern itself with where the page is or something like that. It just says here's a range of virtual addresses. I just want to put 0 there, and that's it. In fact, this macro just calls memset, nothing else. So we'll discuss that in more detail very soon. We'll look at page dynamics. So if the value bit is 0, it means the CPU doesn't read the rest of the bits there. The CPU says, hey, I have no idea what that is. I'm not going to look at that. If it's 0, it's an exception. That's it. And so it means that the rest of the bits are now free to be used by the memory manager. So the memory manager actually uses these bits in a proper way, such as I mentioned demand 0 just now. So it has the flag that says, hey, that's going to be a demand 0 page. And also, if you look at a case where the page is actually in the page file, the memory manager needs to know where is it in the page file. So in what offset of the page file is the file at? So where would the memory manager store this information? So one way is to have some crazy other table that maps every invalid PTE to where it's stored on disk. That could work, but it's very wasteful, and we don't really need it because we can store the offset to the page file right then and there, where normally the offset to the physical page is stored. We can store that as a memory manager inside the same PTE. And so once the process accesses that memory, we get an exception. The memory manager can say, here's the location where the page is in the page file, and just get it from there. And so it's easy to just reuse these bits as in any way the memory manager sees fit. Another thing that relates to that is the fact that Windows actually supports 16 page files. And so if I have an offset to the page file, there's not really the page file, there's a page file. And so we need to say, okay, so in which file do you mean? And so here we can see there are 4 bits here that are used as an index to the page file in question. And what I'm showing here is the invalid PTE for the classic 32-bit Windows kernel. Of course, in today's PTEs, they are 64-bit long, but same idea applies. The page file offset is stored where normally the offset to the physical memory is stored, and so that the memory manager can quickly get to the actual data when needed. And so again, these bits are used by the memory manager in any way it sees fit. Okay, so now we can talk about the page files and then look at how physical memory is managed by the system. And so again, the purpose of a page file is to provide backup storage for writable private memory. And so if a memory hasn't been written to, there's no need to use a page file. If the memory is shared, that is a DLL or a mapped file, there's no need for a page file at all for that. So let's say I'm using a DLL. Let's say I haven't used that DLL for a long time. And maybe the memory manager decided that the RAM occupied by this DLL should go away to serve other processes. And let's say that now I access that DLL. I try to call a function that DLL. And so the memory manager now gets a page for it needs to bring back the code of the DLL. Where will it go? It doesn't go to the page file because the code is not there. The code is as part of the image itself. And so the DLLs and executables are backup for themselves. So anytime their code needs to go away, there's no need to save that in page file. You can just throw the memory away and give that memory to someone else, the RAM. And when the code is needed again, you can just read it from the file itself. And so code is always backed up by the image files themselves, which is good. And so the page file is only used for private memory. All the stuff I'm doing, like calling malloc or virtual alloc with memcommit, this is memory I need to save for later if I don't use it for a while. And so the page file is only for private committed memory. If it's reserved memory, there's nothing to save. Reserved memory, there's nothing there. And so again, reserved memory is just the same as free. There's nothing there. I haven't yet described how reserved memory is managed. I will describe that later on. And so Windows supports up to 16 page files. Only 2 are supported on ARM architectures. Sorry, ARM architecture. ARM64 still supports 16 pages. They must be on different partitions, and we can set their initial size and maximum size using the Windows configuration or using the registry. And so first, why would we need more than one page file? So there could be several reasons. One of them, maybe I have 2 disks which are physically different. So they are not 2 partitions in the same physical disk, but 2 partitions on different physical disks. Then it's be beneficial to do I/O at the same time concurrently with these 2 disks. It may be the case that one partition is too full and I want to spread that out to another partition. Maybe one partition has an SSD drive and the other has a normal sort of slow rotating drive, and so maybe I want to put some page file, some small page file on my SSD, which is probably smaller, and then the rest on the other disk. So we can play with that. And so we can set initial and maximum sizes. The name of the file is always pagefile.sys. It's hidden in the root partition. We can always, of course, look at that. It's created contiguous on boot with the initial size if possible. This is especially important for non-SSD drives where we have that head that is moving like crazy, and so we want to create that contiguous in the physical sectors of the disk so that that seek time is going to be less than usual. And the usual question that comes up is, what should the page file size be? And unfortunately, in earlier versions of Windows, the values that are set for a default sort of telling the system, hey, please take care of that, weren't very, very good. And only Windows 10 actually solved that problem in a satisfactory way. So let me describe that first. So let's first go to the location where you can configure page files. So I need to go again to my PC properties and then go to the advanced system settings, which brings us this dialog, and then we go to the performance settings and then really advanced and get to this dialog. And so this page we've already seen. We have the upper part which is about the length of quantums, which we discussed already, and now we're going to look at the lower part which says virtual memory, and here we can configure page files. And so by default what we'll see is the automatically managed page file size for all drives, which is the default. It says, hey, I'm going to do that on my own. You don't have to do anything about it, but I can uncheck that, and then for every partition on my system I can set either it to be a system managed size, which is the same as previously, I can say here's a custom size with an initial size and a maximum size, and I can even set no paging files. Hey, I don't need any paging file, thank you, I'm fine without it. And so if you have lots of RAM, it is definitely feasible to say, hey, I don't need any page file, the amount of RAM that I have is good enough. If everything that I'm using doesn't fit in RAM, that's tough luck, that's my problem. So it's perfectly fine to run without a page file if you wish. The custom size allows you to set initial and maximum size. And the way this works is that the initial size is used when the system comes up, when the system boots, and then when you start using more and more and more memory, when the page file is filled and RAM is full, then the page file size is increased to the maximum size, allowing you to make more allocations. And so you get a larger page file. And then you can continue allocating, and if you get to that maximum of the page file, then that's it. You're out of virtual memory, and so any new allocations will start to fail. You start to get null in mallocs and in other allocation functions, and really you should probably close some processes that consuming lots of memory. And so the default that we normally see, this automatically managed page file for all drives, gives us the following options. So in earlier versions of Windows, it wasn't very good. And so it used something like the minimum value being 1 times RAM and the maximum value being 3 times RAM. And so it used the RAM that you have on your system as some form of indication of how much memory you need. But this is really not a good idea. So let's suppose you need for your work 40 gigabytes of memory. That's the memory you need. You looked at that. With all your applications running, you need 40 gigabytes of memory. So if you have an 8 gigabyte of RAM, then definitely you need 32 gigabytes of page file size. Otherwise, you will not be able to allocate to commit 40 gigabytes of memory. But if you have 32 gigabytes of RAM, you only need 8 gigabytes of page file memory. And so basing the amount of the size of the page file on the amount of RAM that you have doesn't really make sense. It really makes sense to look at your usual workload and configure the initial file size to be just like your normal workload, and the maximum size a bit more than that so that you can handle spikes in your work. And so basing stuff on the RAM is really doesn't make any sense. In fact, if you have 64 gigabytes of RAM, do you want a page file of 64 gigabytes? No way. You bought that much RAM, so you won't need that much page file. And so Windows 7 and 8 to some extent use that scheme. Windows 10 is different. Windows 10 uses a different scheme. Windows 10, if you select System Managed, then it actually stores the history of your page file usage of the committed memory you're using for the past 2 weeks, and then adjusts the page file size as needed on the next reboot. And so it actually looks at your real usage of the system. And so that's why today I leave this checkbox as System Managed checked, and also select automatic in the case of memory dump, of a system crash, because I know that this particular option also takes care of that and makes sure the page file is large enough to hold with high probability a kernel dump. And so today this is actually a good option. In earlier versions of Windows, it's not the best option. I typically went into that dialog and changed the initial and maximum size depending on the way that I work with my system. So Windows 10 actually solved that issue. So you can use it out of the box and not worry about it. In any case, every information about the page files is written to the registry, like everything in Windows. And so this UI we've seen just now is just a wrapper around setting some values in the registry. Here you can have a list of page files. For each page file you can you can write, it's actually a string there. You can write the partition name, the initial size, maximum size, and stuff like that. If you specify 0, it says system managed, so I don't want to manage that. The maximum size of a page file today is 16 terabytes for a single page file, and so that's pretty big, so shouldn't be any problem in today's systems. So that's page files for you. The next thing we want to look at is what is commit charge. And so if we go back to Task Manager, we see this thing here that says committed / something here. And so committed here means the amount of memory committed right now on the system. And committed means that this memory is guaranteed to be available if I need it. It doesn't mean every part of this memory is in RAM. In fact, the RAM usage is only 18.7 gigabytes. As we see here, this is the RAM used right now. But if I need to use the entire 24 point something gigabyte of memory, I am guaranteed that this will succeed. Maybe it will cause some paging, maybe not, but it's guaranteed to succeed. The number beside the slash here, this is the current commit limit. This is the amount of memory I can commit on the system before page file expansion occurs. And if the page file is already expanded, then this is the total commit limit that I can get to before I get errors in trying to allocate memory. And so when I'm committing memory and that commit succeeds, it means that the system guarantees this memory will be available whenever I need it. And so if we go back to the example in Visual Studio here, when I committed here 1 gigabyte of memory, what happens is, let me just even run that just to prove that in fact it works the way that I say that it works. And so I'm running that with a debugger, and I want to look at Task Manager in exactly the same time. And so once I execute this line, what do I expect to happen? I expect the commit size to jump by 1 gigabyte because I still have not reached my commit limit. What do I expect about the RAM? Do I expect the RAM to jump by 1 gigabyte? The answer is no, because as we said, there's demand pages here. Once I access the memory, then at least one page will have to be committed to RAM. So some RAM will be used. We probably won't see that because this is only in gigabytes and hundreds of megabytes. So let's try it. Let's F10 here. So notice we get a jump with 1 gigabyte exactly. And so the system guarantees that this pointer P and the 1 gigabyte it points to will be available whenever I need it. Of course, when I access it, some RAM will be allocated, but the fact that it was committed successfully means that RAM will necessarily be available. If there's free RAM, that will be available almost immediately. If there's no free RAM, then maybe someone else would have to throw a page back to the page file, but it will succeed for sure. Okay, so this is the idea of committing memory. This is memory that is guaranteed to be successfully accessed. And so this slide just depicts all the various cases where the commit limit increases. And so I need memory that, if I need it, will work eventually. And so what's the point, question here, what's the point of paging out memory when RAM is available? Who says memory will be paged out? I didn't say that. And the thing is, I'm sure you're referring to the fact that there's 18.9 gigabytes of RAM used, but committed memory 24.3. But so why isn't every piece of memory here is actually in RAM? So there's plenty of RAM here free. I have much RAM free, but really this is not exactly what you think it says. It's actually only accounting for pages that are in the working set. There are pages others that are actually in RAM, but they're not considered part of the working set. This is what we see here in the standby pages. And I'll explain what that really means in a few slides when we discuss physical memory. That's actually a good question. And so we'll get to that. So what we see here is just some ideas of what can cause the commit size to increase. So for example, if I use virtual allocate mem commit, like we're seeing right now in a demo, sure, that will increase the committed memory for sure. Of course, assuming this succeeds. If I use map view of file, which is for file mapping, which we look at later this module, then again, we're going to commit some memory there, then it's going to be part of the committed size. Any copy on write map memory that was used. So we need memory for that for sure. Kernel memory, whether page or non-page, of course, this is part of committed memory. All the stacks, kernel mode stacks and user stacks that are currently used, currently committed. The reserved part doesn't count because it's not used yet, maybe will never be used. And so page tables themselves, the actual page tables, page directives, all these data structures used by the translation mechanism, they also consume memory. They're also part of committed memory. And one of the things that changed in Windows 8.1, which I haven't discussed, is the fact that reserved memory is actually much cheaper in Windows 8.1 than it was before. Because before Windows 8.1, if I reserved 1 GB of memory, then of course that's not committed memory, but the kernel the memory manager would create all the page files, all the page tables entries needed to map that memory as if I would eventually commit the entire range. And for megabytes of memory, even a few gigabytes, that's not too bad because we need a single entry, which is 8 bytes long, for every 4 kilobytes of reserved memory. So that's maybe not too bad. However, if you try to reserve terabytes of memory, like in the case of Control Flow Guard, where we've seen that there's about a 2 terabyte reserve memory, if we would create all the page tables needed to map that kind of memory, eventually, then this will be too costly. In fact, the change made in Windows 8.1 says, hey, you reserved a large chunk of memory. I do not guarantee that once you start committing memory, that you'll be able to commit everything. There's no guarantee. And in Windows 8.1 and later, this is actually fine because Control Flow Guard will never commit all these 2 terabytes of address space. There's no way to commit that much memory in today's systems because we don't have enough RAM and so on. And so, in fact, that change was made for the benefit of Control Flow Guard. And so, in any case, regardless of CFG, any reserved memory today is even cheaper than it used to be. So it really doesn't allocate any page tables, potential page tables, to if committing that memory will be needed later on. And that means we can reserve crazy large pieces of memory without any problem. So here I can say something like this. Let's just reserve, so I cannot commit that kind of memory, but let's just for demonstration purposes, we're going to reserve in this process 127 terabytes of memory. So terabytes is like 2 to the 40th power. So I'm going to reserve 137 terabytes of memory. That's really crazy of me. Let's see if that works. So I can't reserve 128 terabytes, that's too much because that's everything that I have. But 127 terabytes, maybe I could do that. Let's try. And so that doesn't work. It seems that failed. Let me look at the error. And so the error is error number 8. Let's check that out. And so here's error lookup 8. It says not enough memory resources available to process this command. And in this case, the reason is that you cannot get, for some reason, 127 terabytes of contiguous address space. So let's try something less ambitious. Let's try 125 terabytes. Maybe that would be good enough. Okay, let's cross fingers. So now it works. So I get the proper value in P. That's 125 terabytes of address space now consumed by this reserved memory, but it's very cheap because there's nothing there. It's just a contiguous region that new allocation will not be able to use in this particular process. If we go ahead to VMAP and look at that, let's select the process. That's going to be our handles process here. Let's see what we get if VMAP can handle that. So here it is. And so, now, still working, thinking. We could, of course, look at Process Explorer for now and find that handles thing. Notice the virtual size. The virtual size is enormous. That's the 125 terabytes of virtual address space. Notice the private bytes is much, much smaller. So we're not even close to using most of this area. And so VMAP is stuck. My guess is that if the process is suspended, it doesn't really like that. Let me try to move along a little bit. Okay, so it managed to sort of put itself out of this mess. And so we can see that this is reserved memory here in the private bytes section, so private data section, because this is virtual alloc function, and all this memory, this tremendous amount of memory is reserved. Notice the free amount of memory is just 3 terabytes or something, which is not as large as in most processors. And so it's really very easy to reserve lots of memory today. It wasn't possible to reserve that much memory in older versions of Windows before 8.1, not just because I didn't have that much of an address space, it was only 8 terabytes, but still, all the page tables memory would be significant. And so the commit limit, the thing that we see after the slash in Task Manager, is the amount of memory I can use throughout the system, which really means the amount of RAM that I have plus all the size of the page files. Okay, so that's the commit charge and commit limit. So anything we're committing, it has to be available when we need it. If it can't, then the committing operation will fail in itself. So I hope that's clear. Okay, so we're coming out to the part where we look at the way physical pages are managed on the system. And the term for physical memory usage is called working set. So every process has a working set. That means the amount of memory that is currently in RAM. So the process may be allocating 100 megabytes of memory, but only 50 megabytes are in RAM. So the working set for that process is 50 megabytes. That's simple. So it's considered part of the memory that is currently committed. So if you look at the total committed memory for a process and the working set for a process, then total committed memory will always be larger or equal to the working set. It can never be the other way around. But the system itself also has a working set. So all the stuff going on in the system process, that means the kernel itself, the HAL, all the kernel device drivers, they also use memory. And some of that memory is in RAM. Some of that memory is not in RAM right now. And so the system also has a working set. There's another thing called terminal services. So for every session, there's actually something that is tracked as well separately as the amount of memory used by a particular session. So some of that is part of working set for a particular session. It's not really important for our purposes. It's an internal mechanism. And of course, in a case when we need to read some data from disk, then the I/O manager, the memory manager, reads more than one page in the hopes that the next data or code that would be needed would be read already, because it's going to read several pages ahead. And that's, again, a good idea, and again emphasizes the fact that contiguous memory is always better than spread around memory. Okay, and so what we have in Windows is something called the page frame number database. What we've seen so far is how a virtual address space is managed. So in a virtual address space, we have free pages, reserved pages, and committed pages. That's fine. But what happens with RAM, with all the pages in RAM? They need to be managed as well. So the system needs to know which pages in RAM are free, which pages in RAM are used, and if they're used, what's their usage count, because we need to know when this page can be repurposed for some other purpose. And so to manage all that, there's a separate database managed by the memory manager called the page frame number database, so PFN database. This is the list of all pages, of all physical pages in the system, and the state of each one of those. So the more RAM I have, the more of these management entities that must be in the system. And so the thing is, we can think of that as PTEs that are valid are pointing to the PFN database. They point to a particular page in RAM, and also indirectly point to that particular data structure that manages that particular page in RAM. And so there's a small data structure, it's about 32 bytes, I think, that manages every page in physical memory. And so there's a question here. So if we add virtual memory, like committing memory, does that mean we're adding physical memory? The answer is no. Like I mentioned, it's only adding that physical memory when we actually need it, when we actually access the memory. But it means that that physical memory will be available for sure. But I am increasing the load on the system. This is what that commit limit is. The commit limit says, hey, up to that point, up to that number, you can continue committing memory. And I guarantee if you need that to be in RAM because you're accessing that, you're going to get it. Maybe there'll be some paging and stuff like that, maybe some I/O, but it will succeed. So it's going to be transparent to the calling code. And so every PFN entry is about 32 bytes in size that manages every 4K of physical memory. So the fact that I have more RAM also means I need to have more memory management objects, and that again kind of that's life. And so the PFN itself can also points back to the PTE from which it originated. And so we can go in both ways. And so the memory manager does that when it needs to update stuff, when memory kind of moves from one process to another, or page gets paged out and stuff like that. So it needs to have these sort of pointers back and forth to change the appropriate values. And the structure layout of that PFN entry really depends on the actual state of that particular page, whether it's free or used, shared or not shared. And that's to try to conserve memory as much as possible. So the PFN is handled like the structure is like a union. Its data means something else depending on what type of page it is, because we don't want that management unit to be large. And so it's kind of packed in there. And I'm not going to describe the various types of PFNs, what they look like. It appears in the Windows internals book. You can read about that if you're interested in. In any case, you can go to the debugger and say something like PFN. PFN says, if I look at PFN number 7, for instance, I'm asking the system, asking the memory manager, what's going on with page number 7 in RAM? Is it free? Does it belong to process A or process B? Is it private? Is it shared? And so on. And so PFN in the debugger is a way to query the PFN database. So I can say PFN number X, and that X can be from 0 to the amount of RAM that I have, of course, divided by the page size, by 4K. So the more RAM I have, the more PFN indices I have. So I can ask the kernel what's going on with PFN index something. The memusage command allows you to get a summary of all the pages used in terms of physical memory in the system. And so this, I think this command is fairly slow. And so if you want to run it, just be prepared to go have a really long cup of coffee, preferably lunch, because it takes lots of time. And so I think it's less useful. It's perhaps interesting, but less useful in a sense. So you can think of the PFN command as sort of the opposite of PTE, or the opposite of V2P that I described and shown earlier. It's kind of looking the other way. For a given physical memory, physical page, who does it belong to, if at all? Okay, and this brings us to physical page dynamics and how physical pages are managed in the system. And so it will be very simple to say, okay, either a page belongs to a process or it doesn't, and that's it. That would be very simple to do, but it's very naive and would cause many hard page faults to occur, which is never a good idea. The management of these pages tries to minimize hard page faults, which are very expensive because I/O is very, very slow compared to anything else. And so soft page faults are fine because they're quickly handled. Hard page faults are bad. And so to do that, the memory manager uses a set of lists, a number of lists. Let's describe that list and the transitions that are happening within this list. So the first list is called the bad page list. The bad page list, as its name suggests, are a list of physical pages that are deemed defective from startup. So the BIOS, the UEFI, whatever, detected some pages to be just physically bad, and so they're sort of out of play. They're not going to be used. I will say that they actually are used today in Windows 10 for memory enclaves, for pages that are part of memory enclaves. I'll describe briefly memory enclaves at the end of this module, but they are not really used, this bad page list, from a dynamic perspective. And again, I'm stressing that this thing that I'm going to describe now is about physical pages only. It's how the system manages physical pages, not the virtual address space of processes. Another set of lists that we have is just the working sets for a process. So the RAM used by various processes, the various pages that are part of some process working set. So we have those lists. Every process has its own set of pages. Some of them may be shared. Some of them may be shared with other processes, such as when code is used by DLLs or executables. And then we have a list called the free page list. The free page list contains pages that are free to use, and so they don't belong to anyone at this point, and their content is garbage. And so there's just junk in these pages. And then we have another list called the zero page list. The zero page list is used to store pages that are free to use, so they don't belong to anyone, but they're all filled with zeros. And what happens is that we have a thread, which I briefly mentioned in module 3, called the zero page thread, whose purpose is to take free pages and turn them into zero pages. So just zero them out. This thread works at priority 0, and it's the only thread that is allowed to work at this priority, which means it can only wake up if there's at least one CPU which is idle, that does nothing. And so its purpose is to provide 0 pages. And so the free page list can actually become 0 in size if all the pages get converted to 0. So why do we need this kind of 0 pages? So one of the main reasons is that demand 0 page fault I mentioned earlier. So if I call the virtual alloc function and commit memory with virtual alloc, I'm guaranteed that that memory that I'm going to get when I access the memory is going to be with zeros. So there's no reason, for instance, to zero out any memory retrieved by virtual alloc with memcommit. There's no need to do that. It's just wasting CPU cycles. The memory is guaranteed to be 0. This relates to a feature that Windows supports in its C2 level security that states that there's no way you can get a page that belongs to another process, even if that process is no longer alive. And so you're not allowed to get any garbage page from another process. And this is why 0 pages are more useful than just junk pages that are in the free page list. And in fact, there's no benefit to the free page list anyway. So you may think, well, what happens if, for instance, the system is very busy and the 0 page list diminishes to 0 size because many allocations are happening and accessing memory and so on. And now some thread calls virtual alloc and requests memcommit and then tries to access that memory, and there are no 0 pages left. And so in this case, the memory manager will take a page from the free page list and zero it out explicitly at that point and then hand it back to the process. So even if the 0 page thread is not allowed to run for a while, even if the 0 page list is zeroed out, that is, there are no more pages there, there's no way a process can get a garbage page using virtual alloc. Now, by the way, if you've used other API functions such as malloc and stuff like that, you may know that this is not the case. You don't get zeros. There's no guarantee, and that's fine, because eventually, when we understand how malloc works, you'll see that eventually it just gives you some memory that you used previously. So it's your own memory. It's your own garbage, so to speak. So that's fine. That's never a problem. You already had that data anyway. The problem is having access to data from other processes. This could never happen. Even if it's garbage and perhaps the process doesn't know how to interpret that, still, that can never happen. So that's the zero-page thread, just making sure the zero-page list is as full as possible. Next, one of the transitions that can happen is when a process terminates. When a process terminates, all the RAM or the working state was using for private pages are not needed anymore. So shared pages cannot be thrown away because they're still used by other processes, maybe DLL code or EXE code. But private data that is currently in RAM is completely useless now. The process is dead. And so these pages just move on to the free page list. So they're garbled, and hopefully fairly quickly they will become zeroed and go to the zero-page list. And so if we look at these kinds of transitions, what you'll find is this free page list is only momentarily going to be above zero and then zeroed out pretty quickly. I'll show you that in Process Explorer after we're done with this slide. So that's one transition that could happen. Another thing that could happen, which we mentioned right now or 2 minutes ago, is the demand zero page faults. So this is the case where I access committed memory with virtual alloc. I committed that memory beforehand, and then I actually do make the access. I need physical page. I need RAM. And that RAM is delivered from the zero page list if possible. If not, then it will be zeroed out explicitly from the free page list. Another thing that can happen is that free pages may be used by the kernel or by read operations from disk. So let's say I'm allocating memory in the kernel, then in the kernel it's okay to get some garbage page that may have been belonged to another process, which may be alive or maybe not. It doesn't really matter, because on the kernel side you have access to all process memory anyway, and so that's not a breach of security. In kernel space you're the king anyway, so that's not a problem. So there's no reason not to use the free page list if it's available. Another thing where free page lists are used or can be used when you read from disk, for example, codes. Let's say I read this code from a DLL, and so the memory manager allocates some RAM to hold that data, and that RAM can contain garbage because in a moment the read operation will kind of trample onto that data and rewrite it with the DLL's code. And so the previous data is just gone, and there's no way anyone can see that in between, because this memory hasn't yet been provided to the original process. This is done automatically, transparently by the memory manager. And so it's completely okay to use the free page because any read from disk would simply just rewrite on top of that. Whether that's code or data from a page file, doesn't matter. So that's also fine. Next we have something called a standby page list, and this is the page list that allows us to sort of have soft page faults if possible. And so let's suppose a process has something in RAM and it hasn't used that memory for a while. And so the memory manager can say, hey, well, you haven't used that for a while. What can we do about that? So one way is to say, hey, okay, let me just take that page away from you, put it in a free page list and forget about it. And so the next time the process does want to access that memory, it will incur a full hard page fault, which will require to get the value of that page from the page file, which is bad. And so instead, the memory manager says, hey, let's just put that onto a standby page list. Would say, hey, you haven't used that page for a while, so I'm going to put it kind of one step closer to being thrown out, but it's not thrown out just yet. The standard page list still remembers the original process to which this memory belonged to. And so if that process suddenly decides to use that memory, then it's brought back to the working set immediately using a soft page fault. So, okay, now you do want to use the page. Luckily for you, I haven't yet thrown it away, so here you are. And so this allows us to have soft page faults that don't involve I/O. Only if the standby page list is very, very big, or the free page list and zero page list become very small, then there's no alternative but to start taking the standby page list and moving them to the free page list to be used by others. And so that's the point where they lose their connection to the original process. If the standby page list is very large, and in most cases it's because the zero page and free pages together becomes very small. It means the system is low on RAM. And so the standby pages, what's special about them is that their state is synchronized with the page file. And so it's okay to let them go if we have to, because there is a copy of them in the page file, so that's okay. If it wasn't the case, then you can't just get rid of them, and instead they'll be in a different list called the modified page list. The modified page list are a set of pages which a process used but haven't used for a long time, and so the system says, hey, that's a page in RAM that you haven't used for a long time, maybe I should take it away from you, but I'm not going to take it away from you immediately, I'm going to put it in a modified page list, and because that page is not yet synchronized with its copy in the page file, I can't just put it in the standby list. Instead, it's in a modified page list. And then what happens is one of two things. Either the process suddenly does make access to that page, and so it goes back to the working set immediately. It now properly belongs to the process because it's now using it. Or if the modified page list becomes relatively large, or the standby page list becomes relatively small, then we have another thread called the modified page writer, which wakes up lazily and then just writes the modified pages to their backup in the page file. And so this thread doesn't wake up often because, again, I/O is expensive. And so it tries to wake up when certain thresholds are met, and it becomes necessary to do so. In fact, there are two threads. One of them is for image files, one of them for mapped files, but it doesn't really matter. And once they're synchronized with their copy in the page file, then they can move to the standby page list. And from there, they can either, again, go back to the working set if the process accesses them, or if the system is low on memory, go to the free page list and just lose their connection to the process. But that's okay, because in the worst case, we'll have a hard page fault that can be handled properly. So that's the main page dynamics that we have using these various lists. And I will get into some more details about these lists after the break. So now it's 7 minutes past the hour, whatever hour it is in your time zone. And so we'll adjourn for whatever we call lunch and continue in 1 hour. So have a great lunch or rest or whatever you do.